Before I ruin your lives with calculus, we need to talk about some functions. Why is this not behaving correctly? Oh no. All right, so the first thing that we're going to talk about is the unit step function. Have you guys talked about unit step functions before? Okay, so we can do this pretty quickly. All right, so the unit step function is also known as the Heaviside unit function, and effectively it is defined as follows. U of t is equal to 1 for t greater than or equal to 0, and it is defined as 0 for t less than 0. So graphically, it looks something like this. So this is just going to be y, this is t, and our unit step function is going to be 0 until we hit t is equal to 0, at which point it is going to instantaneously jump up to 1, and then it's going to continue at 1 in perpetuity, right? So this is a very important function that's used in signal processing things. And in previous circuit classes, we have kind of skirted around, like we've used this without really understanding that we've used it when we played with our switches and things like that, right? So for example, if I wanted to put the signal 5 U of t volts into a circuit's form, it might look something like, here's our network that we would be applying this signal to. Here is our 5-volt source. Here is a short circuit. And then this is what our configuration would look like. So I'm just going to put this as a network over here, right? So before our switch changes states, there is 0 volts applied across our network's terminals. And then after our switch changes states, there are 5 volts applied at our network's terminals. So this is exactly describing what the mathematical function of 5 U of t is doing. So we can relate this back to things that we have done before. We could also figure something out for a current wave, or so a current unit step function, but you guys kind of get the gist of things here, right? So this is our unit step function. We can use the unit step function to effectively turn on and turn off other functions as well. So for example, if I had the following waveform that consisted of a sawtooth pulse, right? So let's call this amplitude is going to be 3, let's make it amps for the sake of argument. And let's call this out here 5 seconds, where this is t measured in seconds, excuse me. And this is current measured in amps. And we had a signal that looked like this. How could I represent this using unit step functions? So what does this section of the line look like as a function? Y is equal to mx plus b format. We just have a simple straight line here, right? There, the intercept is 0. So what's the slope? 3/5, okay? So I would argue that it looks like 0.6 t. We're going to turn it on at t is equal to 0. We're going to turn it off at t is equal to 5 seconds. Right? So we can see here that we're effectively able to time shift our unit step functions, right? Much like we did in circuits 1. Whenever we have a time shift to the right, we get a negative sign. Whenever we have a time shift to the left or in advance, we have a positive sign. Okay, nothing wild or crazy there. So, have you guys talked about unit impulse functions before? Okay. So, a unit impulse function also known as the Dirac delta function, is defined as follows. So delta of t is equal to zero for all t values that are not equal to 0, and it is infinity at t is equal to exactly 0, excuse me. And we can graphically represent this as follows. So here is our generic output, here is time. So we would have simply 0, and then an impulse at t is equal to 0, and then 0 continuing on like so. So, since you guys have seen this before, what's the relationship between the unit step function and the unit impulse function? Right, so the unit impulse function is the derivative of the unit step function. Okay. So du of t by dt is exactly equal to delta t. Now, this unit impulse function is probably more important, at least in my mind, than the unit step function. It has some pretty interesting properties. Obviously, we can time shift things. So if we wanted an impulse at, say, t is equal to 3 seconds, we would have delta of t minus 3 seconds. If we wanted to put our impulse before t is equal to 0, we would have delta of t plus some number. No big deal there, right? But what happens when we multiply a function times a delta function, right? So if we have some generic function f of t multiplied by a delta function, what's the result of this operation going to be? So our Dirac delta function is 0 for all points in time that isn't equal to 0. It's going to effectively sample or sift this guy right here is what it's called. So we're going to wind up just getting I'll make sure I'm doing this right because it's been forever. I believe this is going to work out to be just f of 0, right? So we sample the value when this guy goes off and we're multiplying by 0 at all other points in time, okay? So this is the sifting property of the Dirac delta function or the unit impulse function. Now, why this is particularly important is because we can use time shifting in order to reconstruct literally any input signal into the sum of a whole bunch of Dirac delta signals multiplied by a function, right? So we would sample it at each individual little point in time over a specific interval and call that, or excuse me, be able to reconstruct our input signal as a sum of delta functions. So another reason why the delta function is so important is because a system's response to a delta function at its input has a very special name called the impulse response. We'll call that, we'll give a symbol here in a moment. And the impulse response can be used to determine how any particular system is going to respond to practically any particular input signal by decomposing said input signal into an infinite series of delta functions. So putting all of that gobbledygook kind of in its place, if we have a linear time invariant system, so a linear black box network, linear black box network, and we input a delta function, our output y of t is going to be what we're going to call h of t, where this h of t is known as the impulse response of the system. If we were to take our same linear black box network and apply a time shifted unit impulse function, our output would be the impulse response shifted by the same amount of time, right? Where this tau is just an arbitrary amount of time shift, could be positive, could be negative. Taking this one step further by applying the shifting property, if at our input we have some generic function x of tau multiplied by our shifted impulse function, then our output will be x of tau times h of t minus tau. And taking this a little bit further, if we integrate our input signal, from negative infinity to infinity, so that's our input, our output will be the integral from negative infinity to infinity, x of tau, h of t minus tau, t tau, and we call this operation here convolution. So our input signal x of t is convolved with our impulse response h of t to give us the output of our system. So the convolution operation has the following properties. It is commutative, meaning that some arbitrary function f1 of t convolved with an arbitrary function f2 of t could be expressed as the integral from negative infinity to infinity of F1 of tau multiplied by F2 of t minus tau d tau, or the integral from negative infinity to infinity of F1 of t minus tau multiplied by F2 of tau d tau, which is the same as F2 convolved with F1. So F1 convolved with F2 is equal to F2 convolved with F1. Damn it. Oh, well, I came back on when I was digging for my other adapter. All right. We have the distributive property. So F1 convolved with F2 convolved with F3, excuse me. Or excuse me, this should be plus F3 is F1 convolved with F2 plus F1 convolved with F3. We also have the associative property. So F1 convolved with F2 convolved with F3 is the same as F1 convolved with F2. Sorry, it should be a T. Convolved with F3. We can time shift the convolution operation, meaning that F1 of t minus some amount of time, capital T1, convolved with F2 at t minus some point in time, time shift capital T2, will just give us our output function shifted by T1 and T2. We have an impulse property. So any function convolved with a Dirac delta function just returns the function itself. And we have another one called the width here, which isn't really going to matter to us too much, so let's not worry. All right. So these are the different properties of convolution. This is a linear operation, and so it's used extensively on linear signals. Now, for those of you that have taken Math 245 and understand Laplace transform, you're probably asking yourselves, why the hell are we suffering through this terrible math? And the short answer is that not all systems and not all signals have a Laplace transform, right? So in the field of electrical engineering, convolution integrals are used in filter design, a lot of signal processing, particularly audio and image processing and all that kind of good stuff. They're used as part of control systems and everything. So this is kind of a fundamental baseline for a lot of different things that you're going to wind up doing when the Laplace transform can't be used. So one last thing that I want to point out before we just work some examples, because this is where you guys probably struggle the most, is to point out that in electrical engineering, we are going to be dealing with causal systems. Who knows what that means? Okay, so in a causal system, effectively, we can't have any stored energy or anything like that before we apply a source, right? So effectively, it means that whatever we choose as t is equal to 0 is the turn on point for our system. So we can't have any stored energy or anything like that prior to t is equal to 0. We can't realize non-causal signals either, meaning that we can't observe a signal until we turn it on. So all of our definitions here, from ranging from negative infinity to positive infinity, don't actually make sense for us, because in our application, everything is going to start at t is equal to 0 when we turn stuff on. So our definition for convolution is going to be x of t convolved with h of t will be the integral from 0 to t of x of tau times h t minus tau d tau for t greater than or equal to 0. And we can also call this x of t minus tau times h of tau, because we can swap the order. Okay. All right, so now it's time to suffer through calculus. So all I want to do for the rest of the class is literally just work a couple of example problems. And then on Friday's class, we are going to work more example problems using the technique of graphical convolution. Okay. And then we'll get into Laplace transform stuff. So let's start with a fairly straightforward example. Okay. So let's say that my impulse response h of t is comprised of a Dirac delta function plus the sum of two exponential functions, e to the negative 2t plus e to the negative 3t multiplied by u of t. And my input signal is just a unit step function. So how I like to perform the operation of convolution is as follows, right? So I'm going to define x of tau, right? And I'm going to do that by literally just replacing everywhere I see t with the letter tau. So u of t is going to become u of tau. Now I'm going to define h of t minus tau. And so everywhere that I see t, I'm just going to replace that with t minus tau. Hopefully nothing particularly groundbreaking happening here. So that's going to look like delta of t minus tau plus e to the negative 2 t minus tau plus e to the negative 3 t minus tau, close brackets, u of t minus tau. Let me make that last tau look more tau-like. So just for simplicity's sake, I'm going to call this thing H1. This part right here is H2. And this part right here is H3, because I'm going to be using effectively the distributive property in order to do this math, right? So what I'm going to have effectively is U of t convolved with H1 of t plus, or actually, x of t convolved with H1 of t plus x of t convolved with H2 of t plus x of t convolved with H3 of t, right? So my response is going to be U of t convolved with delta of t plus U of t convolved with e to the minus 2t U of t plus U of t convolved with e to the minus 3t U of t, like so. And now we're actually going to set up our integrals. So before we technically do that, though, what should this first thing be? Right, so if I convolve a unit step function with a Dirac delta function, what do I get? Go back to the properties that we talked about just a moment ago. U of t. So if I convolve anything with a unit delta function or a Dirac delta function, I just get back my original function. So that's going to look like U of t. Okay. Now I'm going to have my integral from 0 to t. So I'm going to have U of tau, that's my x of tau, times e to the negative 2 t minus tau times u t minus tau plus the integral from 0 to t u of tau times e to the negative 3 times t minus tau d tau. Actually, sorry, I need another u of t minus tau. D tau. And I should have a detail there, sorry. So let me ask you guys a question. What does u of tau look like over this interval? 1, right? So this bit right here is just going to go to 1. What does u of t minus tau look like over the interval from 0 to t? So this is a point of time after it's fired off. So this is also just going to look like 1 regardless of what tau is. So we're left with u of t plus the integral from 0 to t of e to the negative t, negative 2 t minus tau d tau plus from 0 to t e to the minus 3 of t minus tau d tau. What I'm going to do now is I can recognize that t is effectively a constant. Okay. So I'm going to break these exponential functions up into smaller parts. Okay. So that's going to look like u of t times e to the negative 2t of the integral from 0 to t of e to the negative 2 tau, positive 2 tau d tau plus e to the minus 3t times the integral from 0 to t of e to the positive 3 tau d tau. Is everybody okay with me splitting up those exponential functions? Hopefully nothing too wild or crazy here. And so now I get to just do simple calculus, right? So I should be able to integrate an exponential function pretty easily. So I'll have u of t plus e to the negative 2t. So what's the integral of e to the 2 tau going to look like? 1/2 e to the 2 tau evaluated at t and 0. Then I'll have e to the minus 3t. And effectively, I'm doing the exact same integral. So this is going to look like 1/3 e to the 3 tau evaluated at t and 0. So I'll have u of t plus e to the minus 2t times 1/2 e to the positive 2t minus 1/2, right? Because e to the 0 is going to look like 1. So I'm going to have 1/2 times 1, something subtracted there. Plus e to the minus 3t times 1/3 e to the 3t minus 1/3. I'm staring at my paper here because it looks like I have accidentally misplaced some u of t's going on, but we know that this thing was evaluated over the interval from 0 to t. So what I am suggesting is that I probably shouldn't have just thrown this thing away and called it a 1 and carried out the u of t. So to fix my jackassery, I'm going to put a u of t here and a u of t here just because I made a mistake because I haven't done this in 5 years. So my apologies. All right, so from here, we can multiply through our things here. So what I mean by that is we'll have u of t. So what happens when I multiply this e to the negative 2t by this term right here? I just get a 1/2, right? Minus 1/2 e to the minus 2t, u of t. Similar thing going on over here. So I'm going to have 1/3 minus 1/3 e to the minus 3t, u of t. And grouping like things together, I'm going to have 1 plus 1/2 plus 1/3 minus 1/2 e to the minus 2t minus 1/3 e to the minus 3t, all times u of t. 1 plus 1/2 plus 1/3 is 11/6 minus 1/2 e to the minus 2t minus 1/3 e to the minus 3t. This whole thing multiplied by a factor of u of t. Okay, so other than my dumb mistake of getting rid of the u of t's before I needed to, so that this actually behaves like a causal system, which it should, math here was fairly straightforward. So let's make things significantly harder, right? So what if we had a similar impulse response? So let's say that yes. So let's say that h of t was e to the negative t u of t, and x of t was sine 3t u of t. So now we no longer have a simple step function as an impulse. We have a sinusoidal signal that was turned on, right? So let me ask you guys a slightly different question here. How is this different than the steady state sinusoidal analysis type stuff that we do? Because a simple exponential response for an impulse function is exactly what we would expect from a first order circuit, so an RL circuit or an RC circuit. How is this input signal different than a steady state sinusoidal input signal? Right. So for a steady state sinusoidal input function, we were assuming that it was oscillating at steady state literally for all points in time, from the beginning of time at t is equal to negative infinity all the way out to the end of time at t is equal to positive infinity. This is more true for a realistic sinusoidal signal where we have to turn it on at some point, right? So we are not going to get just the simple result that we would expect. We're going to actually have some transient buried inside of it because of turning the system on. So h of t is going to look like e to the negative t minus tau u of tau x of tau is going to look like the sine of 3 tau u of tau. And now for my convolution. Yep. Yes, actually, thank you for that. Yep. So y of t is going to be the integral from 0 to t of x of tau h of t minus tau d tau for t greater than or equal to 0. integral from 0 to t of sine, 3 tau e to the negative t minus tau u of tau u of t minus tau tau over this entire interval. This thing is going to look like 1, so let's just leave it like that. And if I'm being entirely honest here, I don't remember the mathematical way to actually resolve this thing. Just looking like my end result looking like u of t. So I'm going to be entirely honest. I'm just going to ignore this step function and put on a u of t again. I don't remember what exactly it's supposed to be. It's a little less bookkeeping that we're going to be doing. All the other stuff will work out, and I'll figure that out. All right, so I'm going to split up that exponential function again. So we're going to have e to the minus t, and I'm just going to pull that thing out so that I don't forget about it, times the integral from 0 to t of e to the positive tau times the sine of 3 tau d tau. So how do I integrate this? Yes, Ryder. Because I'm lazy and I'm just moving this to the outside because I know my answer is supposed to have a unit step function. I can't remember how to do it specifically. Right, which is going to look like a 1. Yeah. So it's going to come out in the wash. I'm just too lazy to remember how to do it mathematically because it's been too damn long since I've had to do this. So I apologize. Exactly right. Integration by parts. Okay, so anytime I have a function multiplied by an exponential function, this screams integration by parts to me, right? So doing integration by parts, just a quick reminder here. So we're going to have 0 to t of u of v prime will be equal to uv evaluated at t and 0 minus the integral from 0 to t of u prime v. That's how I learned it. I'm going to call u sine of 3t or 3 tau. V prime is going to be e to the tau. U prime is going to be 3 cosine 3 tau. And v is going to be e to the tau. So I'm going to do this in blue because we're going to come back and just substitute in here in a little bit. So the integral from 0 to t of e to the tau sine of 3 tau d tau is going to be e to the tau sine of 3 tau evaluated at t and 0 minus the integral from 0 to t of 3 cosine, actually, let me move this, 3 e to the tau cosine 3 tau d tau. Are we okay with that thus far? Anything seem wrong? So e times v, this guy right here, so the e to the t times sine of 3 to the t, and then we're going to evaluate things a little bit later. This will be a more closed form. For now, u prime is the 3 cosine 3 tau. D is the e to the t. Let's do this. How are we going to perform? this in. Also, integration by parts. Yay, it's a blast. It's the best thing ever, right? So just clearly defining things here. U is going to be 3 cosine 3 tau. V prime will once again be e to the tau. U prime will be -9 sine 3 tau. And V will be e to the tau. So we are going to have integral from 0 to t e to the tau sine 3 tau dt will be equal to e to the tau sine 3 tau evaluated at t in 0 minus open bracket. Let's see, 3 e to the tau cosine 3 tau evaluated at t in 0 minus the integral from 0 to t of -9 e to the tau sine 3 tau d tau. Close things up here. Can I screw any of this up? Always a possibility. So just going to double check things here. So u times v, this guy right here, all that seems legit. U prime is the -9 sine. V is going to be the t, so that seems fine as well. That should be fairly obvious now. So this negative can cancel out this negative, so that it's going to look like a positive. So let's go ahead and do that to make our lives a little bit easier. So plus sign here, get rid of this sign there. And then I have a factor of -9, all of this junk. I have a factor of +1, the exact same thing on that side, so I can move that all over and find that 10 integral from 0 to t of e to the tau sine 3 tau d tau is equal to e to the tau sine 3 tau evaluated at t in 0 minus 3 e to the tau cosine 3 tau evaluated at t in 0, or the integral from 0 to t of e to the tau sine 3 tau d tau is going to look like something over 10. That's something. So let's see what we have here. So when we substitute in t for tau here, that's easy. So that's going to look like e to the t sine 3t. What happens when I substitute in 0? It's going to go away because sine of 0 is 0. Right? Now we're going to take the second bit here. So substituting in t is easy. -3 e to the t cosine 3t. What happens when I substitute in 0? It's going to look like 1. So I'm going to have minus -1, right? Because I have this minus sign out here. So if I split that off, I would have 3 e to the t cosine 3t minus 3. And then when I have that negative sign there, it's going to make it look like +3. And now I'm going to take this result and substitute it back in way up here, so that I get y of t will be equal to e to the negative t, e to the t sine 3t minus 3 e to the t cosine 3t plus 3, all divided by 10 u of t. Now distributing through that e to the minus t. So I'm going to have 1/10 sine, sine 3t minus 3/10 cosine 3t plus 3/10, all of this multiplied by you're absolutely right. Thank you for that. I just missed it. Yes. Absolutely correct. Thank you for that. Let me scooch this over. So what Grayson was pointing out is that when I multiply this e to the minus t times this positive 3/10, I should actually still have a factor of e to the minus t. Thank you very much for that. U of t and it should be no trying to think of the words to use here, right? So 1/10 sine 3t minus 3/10 cosine 3t. This is just a simple addition of sinusoidal functions, right? They have the exact same frequency, so we could add those guys together as complex numbers, and we would have the steady state sinusoidal response that we would expect. And on top of that is going to be this transient decay from when our system kicked on, and it's going to die out over time. Right? So it is very similar, but distinctly different than the steady state sinusoidal analysis that we've done before, because it's including the transient. All right, that went a little bit faster than I expected, mainly because I skipped another example problem because I thought this was going to take longer. So let's call it a day here and get out about 15 minutes ago. You guys should have noticed that homework set number 2 has been posted, and I think I have provided you with the answers for roughly 75% of things. I will endeavor to get the answers up for the other bits, probably early tomorrow morning. You probably also noticed that I did not get any videos uploaded yesterday. That's also not going to happen today because I have to go figure out what you guys' lab is going to be like tomorrow. Because we're doing it downstairs in the new power lab, and so I have to make sure everything works.